So I think you are clear with the before session, right? So in this session, we are discuss about quantum threat landscapes, post-quantum cryptography's fundamentals, strategy, transition approaches, and implementation roadmaps, and industry case studies and next steps. Okay, done. So the quantum threat. So already we discussed regarding the threat, how we will be attacked. Okay, regarding all the things. So next, the quantum computing timeline. So how it will be grows. So calculate from the 2023 to 25. So the noisy intermediate scale quantums NISQ era was bit from SU 50, sorry, from 50 to 100 qubits. The system with limited error corrections. So from 2025 to 30, it will be improved into 1000 qubits with the potential to break the risk. So RSA 2048, and it will improve error corrections and scalings. So in the 2030 place, so the it will be acute the fault tolerance quantum computers and practical sure algorithms implementation on all the cases and threatens all public key cryptographies. So this is the timeline of quantum computing after 10 years. Okay, right. Then, so what are the risk factors we have? As I already said, we have national security risk like military, okay, army, DRDO, like intelligence operations. So these risks we have. Next, financial infrastructure risk in the banking, the payment gateways, in blockchains, right? In the currency as well. In the healthcare, already we discussed those things. Like patient records, medical devices, pharmaceuticals R&D's data as well in the risk. The same here the add-on is cloud infrastructures. Nowadays, we are all are using Google Cloud or else Amazon Cloud for the storage. So anyone, even though they don't know the technical things, technical terminologies, they will save their photos into Google Drive, right? So even though we are also using Google Photos, so it will be automatically store your photos. So at the time of storing, there is no glitch. So, but the quantum computers that existed, your data will be stolen. So this is the best example for the cloud infrastructure. So how it will be, we will see. Okay. Then next. So, so in the government, so cloud in the sense, not only your personalized things. In the government also, we have workloads for AWS, Azure. So even though if you have knowledge in NIC cloud, so even though there is a glitch as well. So coming to healthcare, already I said, right? Clear? Next. So for this, we have some things like we have tools for that. So in the IBM, we have a tool for the shores. So it is already developed. The tool name is QuizKit. So it is assimilated to shores algorithm on small RSA. Okay. So same like that, we have a tool that is Warshark TLS Analyzer. So it shows the dependencies on RSA and ECC in real-time profits. Clear? Next. So as I said, the harvest now decrypt later, right? So this is the key takeaway. So harvest now decrypt later is that stolen the data today is a liability to tomorrow. Okay, so it means that what? So stolen data today and it is in a liability of our tomorrow futures. Okay. In example, as I said, Aadhaar linked health records. So it is be going on right now. So before we don't have this. So but it was implemented in 2030. I hope so. So Aadhaar linked health records encrypted today maybe. Take an example. Okay. It will be stolen with at the time of the quantum data is present in the world. Okay. Right. So this is the just vulnerable cryptography standards. So in the RSA, we have RSA and DSA, it is 100%. The ECC, we have it is in 100% only. But in the H key exchange, it is only 65%. Okay, then next. So what is post quantum cryptography? Already we said. Then, but why the post quantum cryptography we need it? So we have to discuss those things here. Okay. So why PQC? Is there any idea in the session, guys? So if you don't have idea, no problem. So I will continue. Okay. So why PQC is means that it is in a classical cryptography. It's in a classical cryptography. So it will change the RSS, ECCs, the HS into broken quantum computings. It will change the systems, all the systems. So that's why we need PQCs, post quantum cryptographies. Already I said, I will discuss, right? Next. So NICT PQ standardization progress. So why we need standardizations, first of all? So as simple as that, we don't have any standardization. Standardization is nothing but an worthy. Okay. So if you take, already we discussed regarding the clock, right? So if you want to take in a lock, if the lock is very loosey or it is not fit the well, is it good? No. If the lock is very standard or if the lock is very strong, only it will protect your house. Then only it will protect your things, right? In the same way, in the same way, in the quantum as well, we need some standardizations. Okay. Further, the National Institute of Standard Technologies (NISTs) has been evaluating post-quantum cryptography algorithms since 2016 to identify the quantum resistance replacements of current standards. So whatever we have before, okay. So for the resolution of the quantum, they will start at NIST. Okay. So already we discussed regarding the things in the 2022. Okay, the 2022 they will launch crystals kyber key and encapsulations. Okay, so in the same way, dilithium we are launched in the 2022 in Falcon as well. Okay, right. So draft standard of timeline. So initially in the 2014 they are published those things. The final standards are expected in 2025 to 26. Federal systems are migration by 2030. It is not done that much earlier. Okay, right. So coming to round four candidates, current we are testing the things. So one is bytecode. It is a KEM thing. Okay. So next one is classical MySQL. Already we discussed this in a code-based KEM. Then next HQC, and it is already a KEM thing. And Psych, this is already a broken thing. So okay, done. Right. So PQC algorithm comparisons. So what's the difference between, we are already discussed lattice based, code based, hash based, multivariate, right? So in this lattice based is nothing but coming to, we have few variations here. So the lattice based is nothing but finding status vectors in the lattices. Okay, the key size is medium from the lattice based. The performance is excellent. The maturity is high. The same way comparatively code based as coming to, it is decoding random linear codes. The key size is very large. The performance is good. The maturity is high. So coming to hash based, it is a collision of resistance of hash functions. The key size is very medium here, and the performance is slow signatures. The maturity is very high. So like multivariate is coming to security bases, solving the systems of multivariate evacuations. So the key size is very large, the performance is fast verification, and maturity is medium. Done? Right. So in the finalist of 2022, we said, right? So what we have, crystal, kyber, crystal, dilithium, and faculin and spinches, right? So these are proved things with using these algorithm comparisons. So these are launched based on these comparisons only. Okay. So in the basis of previous things only, they build these algorithms. Okay. Next, right? So strategic transition of approaches. What we have, so we have a hybrid cryptography. Already we discussed these things. So this is the fastest, safest, and fastest path towards the world. So hybrid cryptography combines. So before we're going to start, so hybrid cryptography is nothing but combination of classic and post quantum algorithms. So it is ensures that the security levels in never fails approach, right? So how it will be safest thing? It means that based on this implementation process, based on the security guarantee process, based on this standardization, it was very safest path. Clear? So that's why hybrid cryptography is very safe thing. Done? Okay. So next, crypto agility and future proofing your security. Okay. The crypto agility is the ability to rapidly switch cryptographic algorithm without significant system charges. Changes. So essential for responding to quantum advances and algorithm vulnerabilities. So we have four things here. One is abstraction layers, another one is pluggable components, and third one is algorithm identifiers, and the fourth one is re-encryption pathways. Okay, so done. So in Indian context, so if you hear any missions like that, so the Indian mission is, so before going to discuss this cryptography, they have an Indian mission that is MITY, so National Mission of Quantum Technologies. It's around started with the 800 crores. So ISRO started in a communication satellite that with quantum, and the Q Noob Labs. So in Bangalore, this is the first quantum security startup. Okay, these ISROs, QNLOOPs, and METs, why? These are all are followed these crypto abilities. So why? Because this is the future proofing your security. So that's why they are followed this all the components. Okay, next. So what are the tools they are used for that? They are used some tools for these things that are open quantum. So that is LibOQs or OpenSSL or OQS. Yes. So next thing is, okay. The next thing is that zero trust and layered defense models. Zero trust and layered defense models. So here zero trust have some principles. So in that the principle, the very explicitly things. It means that never trust, always authenticate. It means that don't trust anyone. So you should be authenticate. Then only it will be work. Okay. So even though nowadays we are following in our things, in that we are following this thing in your mobile phones. Okay, your mobile phone sensor is there na, there is never trust you. So if you are authenticate personally, it will allows you. In the same way, they will implemented zero trust in quantum layers. Okay, so this is the apply latest least privilege access. Okay, then next, assume breach has already occurred. So it gives a what? It gives an impossible creative to the world. Okay, so zero trust models are reduce the impact of cryptography failures by limiting the scope of duration of access, even with valid credentials. Okay, so layered cryptography defense is that says that multiple independent cryptographic boundaries, and it says that different algorithm families at each layers, and separate keys of security domains, and quantum resistance key derivation functions. Okay, so implementation for the roadmap. So we have some implementation roadmaps here. So that is step by step migration. Okay, so here the thing that involved in the